Okay, good morning. All right, let's try that again. Good morning. Oh, that was good. Really, really good. Okay, so first of all, I pulled up the course calendar. I want to point out that next Monday, September 5th, is Labor Day. So we all get a day off. Yeah, I think we all need that day off. It's good. Okay, so don't come to class on Monday. And today we're going to look at section 13.2. And we're finally going to be doing a little bit of calculus with vectors. We'll be looking at derivatives and integrals of vector functions. So first of all, the derivatives of and integrals of vector functions are defined pretty much the same way that we calculated them for scalar functions. So recall that for a scalar function, y is equal to f of x. The derivative is dy dx, or y prime. Remember, the definition is the limit as h goes to 0, f of x plus h minus f of x over h. And you remember that this is just a slope between 2 points, and then h going to 0 means we progressively bring the 2 points closer and closer together. In the end, we ended up getting the derivative of that function. Pretty much the same idea when it comes to vector functions. For a vector function, r of t, and let's say it's a three-dimensional function, and the x component is f, y component is g, and the z component is h. The definition of the derivative of r of t, a vector function, follows exactly the same line. So derivative of r, the r dt, or r prime of t. Now remember that this is a vector now. And it is still the limit as h goes to 0, r of t plus h minus r of t over h. Right? So fundamentally, you treat this vector function essentially exactly the same way as a scalar function. You're taking two vectors that are a little bit apart and gradually bring them together, and you end up getting the derivative of that. This is also equal to the individual component, and you take the derivative individually. So this will be equal to f prime of t, g prime of t, and h prime of t. Okay, so for a vector function with scalar components, it's always the case. The derivative is simply the derivatives of the individual component, one at a time, in their own place. And rules such as product rule, quotient rule, chain rule, and so on still apply. In fact, they're still the same thing. In the end, you're taking the derivative of scalar components, and it's a part of a vector. So everything you know about differentiating f of t, whatever f is, still applies. One quick example before we find out what r prime of t does. So here's my vector function, t e to the t squared plus 5t, and t cosine of 3t. And let's find the derivative of that vector function. Okay, so now you're doing the derivative 3 times, once for each of these 3 components. Do you remember how to differentiate t times e to the t? What rule do you have to use? Right, product rule. Right? 2 functions of t here multiplied together. So it goes the first times the derivative of the second, e to the t. What's the derivative of e to the t? E to the t, good. And then the second part of the product rule is the second function here times derivative of the first, and that's a 1. This one is easy. That's just a polynomial, 2t plus 5. And here, product rule one more time. It's the same situation as the x component. The second function becomes a cosine instead of e to the t. All right, so first, this is the first derivative of cosine of 3t. What do we get? Negative 3 sine 3t, right? Negative 3 sine 3t. Where did that 3 come from? Chain rule. What about the negative? Derivative of cosine is negative sine. Very good. And then the second part is cosine 3t plus derivative of t, and that's still just 1. All right? Okay, now let's find out what exactly this r prime of t looks like. Let's go back to the scalar function again. For a scalar function, y is equal to f of x. And let's say y of f of x looks, let's just make it a parabola. And let's say that point is at x is equal to a. And you should remember that this red line, the tangent line, has a slope equal to f prime at a, right? Derivative of the function at the number x is equal to a. Remember that? Okay, that's the same idea here. Now, imagine this is not a scalar function, but a vector function. We're still going to get some kind of tangent thing out of it. And this time, instead of just a slope, we'll get a vector. For a vector function r of t, And you remember from last time, R of t describes a curve, a space curve. And if you go to t is equal to a, for example, right here, what you will get out when you take the derivative is a vector that is tangent to the space curve at t is equal to a. Okay, so the space curve, if you take the derivative at any point, at some other point here, let's say, we'll make this t is equal to b or whatever. This vector here is r prime of b. So just like the scalar case, you get, when you take the derivative, you get a tangent line with a certain slope. The slope is what the derivative gives you. Here you get a vector coming out of that. And notice that the vector in general is going to have different magnitude depending on the derivative of r. Let me give you one example that's a little bit more concrete than that. And let's look at a two-dimensional vector here. For one thing, it's easier to sketch. For another, the idea is the same. Okay, so my space curve is r of t is equal to cosine of t, sine of t. So the x component for any t is cosine of t, and y component is sine of t. What shape is this? Circle. How do we know that? Yeah, we did something like this, very, very similar to this last time. Remember, this is x, this is y. And we know that sine squared of whatever plus cosine squared of the same whatever is always equal to 1. So this implies that this is x, right? This is x squared. Sine is y. This implies that x squared plus y squared is equal to 1. And that we know is a circle with a radius of 1 and centered on the origin. There we go. There's our circle. This is a space curve, so it has a direction of motion. In what direction are we going around the circle? Clockwise or counterclockwise? Counterclockwise. How do you know that? If we assume that this is t equal to 0, that's 1, 0. As you increase t, cosine will get smaller initially, and sine will get bigger initially. So we know we're going in this direction. At t is equal to pi over 2, for example, we know cosine is 0 and sine is 1. So you could also figure out that if I start here and I end here, I must have gone in this direction. You can find t is pi over 4 and so on. So in various ways you could figure out the direction in which we travel around that space curve. Let's take the derivative of this. R prime of t is a vector. Derivative of cosine is negative sine, and derivative of sine is positive cosine. Let's go to t is equal to pi over 2. Our prime at pi over 2 is -1, comma 0. Okay? So this tells you the vector that is tangent to the curve at t is equal to pi over 2. Pi over 2 is right here. And the vector tangent to the curve has an x component that's -1. That means I go to the left. And the 0 y component, so we don't go up or down. So that vector is going to look like this right here. Does that make sense? And similarly, this vector right here, this would be r prime at pi over 4, right? The vector from the origin to that point, that's the position vector, r vector. R at pi over 2, pi over 4 is a vector from the origin to that point on the space curve. And the derivative of that vector function is tangent to the green curve, the space curve, at that point. For a circle, these two things are always perpendicular to each other. But in general, these two are not perpendicular. For a circle, it is true, but not in general. Questions? All right, let's try a three-dimensional one. Cosine t, comma t, and then sine of t. You remember the shape from last time? Not a cylinder, close. It's a helix. It's a curve that's on the surface of a cylinder. Right. This was a helix. And once again, if you had trouble seeing that, we see from here that x squared plus z squared is equal to 1. So looking at x versus z, we see a bunch of circles. But the y component is growing with time. So you have a circle that's being stretched out as time goes on. All right, so what does this look like? This will look something like that. And it's going toward the positive y direction. Okay, let's take the derivative of this. This is easy. Minus sine, positive 1, and positive cosine. So once again, this will give you a vector that's tangent to the helix at any value of t. For example, r prime of 2 pi is 0, 1, 1. All right, so let's figure out where that point is first. The position at 2 pi is 1, 2 pi, 0. So 1, 2 pi, 0 is right, let's say right here. This is the point, 1, 2 pi, 0. And then at that point there, the vector that's tangent to the curve is 0, 1, 1. There's no x component, so it doesn't come toward us in this view here. It has to go to the right and up, right? And if you look at that helix here, it's going to have to follow that helix shape. So it's going to go something like this in that direction. In other words, r prime of t tells you in what direction, if you're controlling that object, in what direction you need to steer in order to complete that helix shape. That's the direction in which you need to aim at while you go to result in this shape. And we have the ingredients to find the equation of the line tangent to that point. We have a point, we have a vector telling us the direction. We can use the vector form of the equation of a line. There's our point, there's our direction, which is given by the derivative here, 0, 1, 1, right? So r sub 0 is the position vector from the origin to this point, 1, 2 pi, 0, plus t is some parameter, and v, the direction of the line, that's the derivative, 0, 1, 1. And that line will extend forever in both directions following that vector. Questions? Yep. This guy right here? That's a vector. The magnitude is the length of that. So square of 0 plus square of 1 plus square of 1 under a radical. Right? So this is a vector with certain magnitude and in a direction. Does that answer? Okay. Other questions? Yeah. Oh, good question. Well, what do you think? What do you think? If, for example, if r describes the position of this red dot, what do you think r prime is? Velocity. We'll actually have a deal with velocity and position in much greater detail in the future, I think next Wednesday. So, but right now we can talk a little bit about that. Don't worry too much about position and velocity right now. But If r is the position, then r prime is the velocity. And so what's the magnitude of velocity? Speed. So that's how fast at that moment that little red dot is traveling, the speed of that object. Again, we'll have a whole complete lesson on position, velocity, and acceleration either Wednesday or Friday. So don't worry too much about those things right now. All right, other questions? Okay, now let's look at a few rules of taking the derivative of vectors. And most of these are very intuitive and make sense just by looking at it. And there's really no reason to memorize these. Like I said, most of these make perfect sense and are very obvious. If you want to take the derivative of two vectors added together, you simply take the derivative of the individual vectors and then add them together, right? It's just like how you would deal with scalar functions. Derivative of f plus g is f prime plus g prime. Derivative of a constant multiple of a vector is the same constant times the derivative of that vector. Again, that seems very, very obvious. Behaves just like a scalar function. If you're multiplying a vector by a scalar function, so some function f that's not necessarily a constant times a vector. Now, this is a new situation that we haven't seen before. But the way you handle this is using the product rule. You take the derivative of f, multiply by the vector, and then you leave f alone, multiply by the derivative of the vector. Like I said, it's just like the product rule. And the order doesn't matter, right? This is addition here. So you could have left f alone, take the derivative of u first, and then add it to derivative of f times u. The order is not important. The derivative of a dot product of two vectors, u dot v, and once again you use product rule for this situation, but instead of a regular multiplication you use a dot product. So this is equal to u dot v prime plus u prime dot v. Again, exactly the same as the product rule that you are familiar with, except instead of regular multiplication, we do a dot product between two vectors. Do I get a vector or scalar out of this? Scalar, that's right, because dot product is a scalar. This right here will be a scalar function. Derivative of a scalar function must be a scalar. So the right-hand side will always give you a scalar in this case. In these two cases, the order is irrelevant. Because you know v dot u and u dot v are the same thing. So if you switch the order of these two, switch the order of everything, nothing changes. Same thing here. Then the last one here we're going to be looking at this. In this case here, the cross product, the order is important. You know that u cross v and v cross u are not the same thing. One is the negative of the other. And in this case, we have to take the derivative in the right order here. Derivative of u crossed with v, no derivative, plus u crossed with v prime. And this will give you a vector at the end. This is a vector, scalar, vector, vector, vector. Yeah? Yeah, these two addition you can, right. But we can't, v cross u here would be the negative of u cross v. So depending on what the components look like, it may not be that big a deal. But the important thing to keep in mind is that the order is important. We can't do a v cross u. Even, I guess the point is the previous two, we can do any order, but this one we got to be really careful, depending on what the components look like. Okay, now let's look at integrals. The derivative gives you a tangent. An integral, this is a little, not as obvious what you end up getting. If R is f, comma g, comma t, then the integral of R is what you would expect. The integral of f, the integral of g, and the integral of h. But you remember, when you integrate a function, you always end up with a constant of integration. Same thing here. You will end up with a constant of integration. But that constant will be a vector. This is a vector constant of integration. It would disappear when you take the derivative of that. So when you integrate, you got to add it back on. But otherwise, it's treated exactly the same way as the same way you would take the integral of. Let's do an example. T e to the t plus cosine of 3t. When you integrate that, you integrate the components one at a time. And what's the integral of cosine of 3t? Positive or negative? Positive sine of 3t, and by the chain rule, we need a 1/3. And now we need to add a constant of integration. That's a vector. So this thing has 3 components. Just like the vector you integrated. Right? So let's call the components C1, C2, and C3. And you could add them together if you want to and get t squared over 2 plus C1, e to the t plus C2, 1/3 sine 3t plus C3. So notice that another way to look at this constant vector is that when we integrate each of these scalar functions, we get one constant. So when we integrate t, we get t squared over 2 plus c1. And that c1 is in the I component of that vector. When we integrate e to the t, we get e to the t plus c2. And that c2 is in the j component of that. Same thing with that c3. So we could choose to take these 3 out and leave them as a separate vector. And these guys don't have the constant. In any case, we need a constant vector whenever we integrate a vector. So that covers the indefinite integral. For a definite integral, let's go back to the scalar again. When you integrate something from a to b, you get capital F, where capital F prime is the little f, at b minus f at a. What's this formula called? Do you remember? Fundamental theorem of calculus. Good. Yep. This applies directly to a vector function. If you integrate from a to b of some vector function r of t, you get big R at b, a vector, minus big R at a, where big R prime is equal to little r. And these are vectors. Okay? So for example, if I integrate the tangent vector from a to b, then these big R's are just a regular R. So this is saying that if I integrate a tangent vector from t is equal to a to t equal to b, the end result is a difference of 2 position vectors. Okay, let me give you a concrete example here that you can see this situation a little better. Let's look at that circle we looked at earlier. And earlier we got that the tangent vector at all t is equal to negative sine, positive cosine. And I'm going to sketch just a portion of this, the first quadrant portion of this. This starts at t is equal to 0, ending at t is equal to pi over 2. Okay, let's look at the integral of this. The integral from 0 to pi over 2 of r prime of t is equal to the integral from 0 to pi over 2 minus sine of t dt, comma, integral 0 to pi over 2 cosine of t dt. Okay, we integrate the components. And when you do that, you don't get a constant anymore. You just get a number, right? So the integral of minus sine is positive cosine. Cosine of pi over 2 is 0, and minus cosine at 0, that's negative 1, so that's a positive 1. Here we get sine of pi over 2 minus sine of 0, which is a 1 again. Okay, so what does this tell us? What we're doing here with an integral here, what an integration is doing is accumulating all of these little tangent vectors. So all of these red ones are the tangent vectors from 0 to pi over 2. Accumulates all tangent vectors. In a way, you're adding them with some kind of change in the magnitude. But by the fundamental theorem of calculus, this vector is also equal to the position vector at pi over 2 minus the position vector at 0. So this vector that goes straight up, this is the position vector at pi over 2. And this is the position vector at 0. Right? So when you integrate all these tangent vectors, what you ended up getting is the difference of these two vectors. This guy minus this thing. And that vector will end up looking like this. This diagonal one. If you think in, yeah. It should be, this is part, yeah, you're right, it should be negative, sorry, it should be negative 1, I'm sorry. Sorry about that, it is negative 1. So what this is telling you, if you think in terms of velocity again, the integration here is just taking all of these velocities and shove them together, accumulating all of these velocity vectors. And the end result is equal to the vector you would need to the position vector, the vector you would need to take to go from where you start to where you end, that diagonal path here. And in the lesson, when we deal with position, velocity, and acceleration next week, you'll find out that this has some relation to the average velocity versus the instantaneous velocity and all of that stuff. Some kind of averaging in some way. This also has application in physics when it comes to work, for example. Only the end and the beginning matter. But we'll leave that to a future part of the lesson. For now, all you got to take away from today's lesson is that you can integrate and differentiate vectors pretty much the same way you already know how to do with scalar functions. Okay, that's it for today. Have a good long weekend. See you again Wednesday.